So today, so we are going to talk. See, we want to discuss the next topic, and we want to go to the next third paper of KRP in this series, and we want to discuss what are called Gaussian channels next. Gaussian channel is a completely positive map which preserves the identity and which preserves the trace. Okay, so I will come to that later. To study that, we need to study something called symplectic. These are all in the matrix theory, symplectic dilation. These are all matrix theory. So what is called symplectic dilation? So dilation is something in general. This is a very important topic in operator theory. Indeed, it's an important, it's a very good industry for those who do research. I mean, you can make a career out of it. So if you have some operator, some A is an operator on B of H. If you have any operator on B of H, okay, it has something. Then we say something is a dilation if we can, so B of H naught, let me say. Then you take a bigger space, H naught, direct some H1 or something. And if A tilde is an operator in B of this, such that if P is the projection from H direct some H to H naught, okay, such that P, A tilde P will be A. That is, this A tilde will look like this, A, B, C, D. Where you know that A is an operator on B of H, B is an operator from B of A is an operator on B of H naught, and B is an operator from H naught to H1, C from H1 to H naught, D is an operator on H1. Okay? So you can write it like this so that it sits as one diagonal entry. This A sits as a diagonal entry. This is what is called dilation. Of course, anything can be dilated to anything just like that, but we need some important good properties. Okay, so we would like the dilated operator to have some nice properties. For example, if A is just a if you have some operator, then it can have some norm. You can divide it by the norm of the operator and you get a contraction. Okay. So if A is a contraction, then we want to see that whether it admits a isometric dilation, so that you can write it as, so that you can amplify it to a bigger Hilbert space and see whether you get an isometry out of it. Okay, that is what is called isometric dilation, and it is indeed possible, and there is a big theory about it. And you can talk about more things. You can take a collection of operators, A1 up to AN. They may commute with each other, not commute, or something commute under some condition. Then whether you can dilate it through a single Hilbert space. These are all some questions. Okay, so whether isometry can be dilated to unitary, all these things whether you can take it to a bigger Hilbert space so that it sits as in one corner, so that this original operator sits in one corner, and whether that whether that dilated operator has a nice property. Okay, so this is what is called a dilation. Here we are dealing with finite dimensional theory, and that is H0, H1, all these things are finite dimensional. And then our what we are interested is whether A admits a symplectic dilation. A is some matrix, whether we can go to a bigger Hilbert space, and you can see whether you can get a symplectic operator out of it. So that is indeed true, and that is what we want to prove the theorem. Okay. So before that, before even stating the definition of a symplectic dilation, we have to make a change of notation. I mean, that is not, which we are forced to do. So for us, this J2 is just 2 cross 2 matrix, 0, -1, 1, 0, as before. Okay. But then J2n is just J2 return n times. Okay.
So P is just a projection.
Yeah, P is just a projection from. So that's why you get it as a corner. That's all. You may even dilate. Sometimes people may like to have the B in the wherever the off diagonal. There you want to keep an operator. For example, if you see, dilation theory is not just for Hilbert space. You can take B of H. You can have operators on B of H, like completely positive maps and all those things. Okay. So there, if you want to dilate a completely positive map to something called completely bounded map, then that is possible if you keep it in the off diagonal. So there are, it's not that you will always see, It is just you want to have it as one matrix entry, and then you want to get it as a bigger operator. So this is a big theory, okay, and you can keep on relaxing condition. You can keep on writing papers on that. So that's there are too many papers on that. So too much work done. So here we are interested in the symplectic dilation. Okay. So the change of notation is the following. Earlier, our J operator is this. J at the n cross n, I mean 2n cross n J operator is 0 minus I 0, right? This was our operator. Here we are writing it as J2, which is off diagonal matrix minus 1, 1, and then we are writing J2 like this. The reason is how you identify Cn with R2n. Okay. Cn to R2n, how do you identify? So you will have xi plus iyi, xj plus iyj. He is already there. So n equal to j equal to 1 to n. This will be identified with earlier x1 up to xn, y1 up to yn. Okay. Now we are identifying with this x1, y1, x2, y2, and xn, yn. The reason will be clear when we make the definition. Okay. So definition. So for us, a J2n is just the, it's not a diagonal matrix. It is a direct sum of J2s n times, where J2 is a 2 cross 2 matrix with off diagonal entries minus 1, 1 and 0 elsewhere. So the definition. So we always deal with 2n cross 2n matrices. Okay, A is a M2n R. Incidentally, there is no change in the Fock space and all those things, that theory. Okay, because there we are considering Cn. This Rn does not play a role at all. This R2n does not play a role in the Fock space theory. Okay. Rn has a role, but that's a different Rn. I mean, this is not this R2n. This identification of Cn and R2n does not really play a role in the Fock space theory, because we are this is just to study these matrices, symplectic matrices and other thing. I mean, considering for our convenience as R2n matrices, matrices with real entries. Okay. So it is because of that. Okay. So otherwise there is no other reason. This. So I forgot to add something. So when we are identifying this Cn with Rn using this map rather than the keeping the x and y's below, when we write like this, then of course then the new symplectic definition will also change. Okay, where sp2n as matrices, we have a one-to-one correspondence between them. A unitary will add you will map those matrices together. So this is all those matrices A in M to N are such that A transpose, maybe L, we put L. L transpose J to N, L equal to J to N. Okay. We can't use the, I mean, this is our new definition, and with respect to this J to N, we define the symplectic operator. And because the identification is like this, will precisely, I mean, this is how we got this is precisely when you write the corresponding complex, I mean, the corresponding real linear operator in the complex space, then that will preserve the imaginary part of the inner product. Okay, that's clear. Okay? The same idea, the same.
So, but like this L, if you look at the complex operator it represents,
L tilde, yeah.
Is L tilde constructed the same way?
It cannot be the same way, no? Right. This, yeah. So under this identification, you have to do. I mean, you have a map from Cn to R2n. Using that map, you I mean, it's clear. From that map, you decide consider this, right? Okay, so this is all the spin group. Okay. Now we make the definition. A is a matrices M2n, 2n cross 2n matrix over R. Okay. Then an A tilde in the spin group, spin of 2n plus 2m, maybe 2m plus n. Okay. is, which is a symplectic operator, which is in the spin group sp2n plus 2m, s2n plus m. It's a two, is a symplectic dilation of A if A tilde looks like this: A, B, C, D, where of course A is in M2n and B is in M2n cross 2m, C in M2m cross 2n, and D in M2m, right? Okay, the corresponding things. Okay, so that A tilde looks like this. Okay. And we also say that this A tilde is a symplectic dilation of A. And in particular, we say, in this case, this is a symplectic dilation of order 2n plus m. Okay, this is what is called the order 2n plus m. A tilde is a symplectic dilation of order 2n plus m of A. If A tilde has the matrix dimension, the Hilbert space where it is acting is 2m n plus m. In this case, we say A admits a symplectic dilation. There may be more symplectic dilation. Okay, we call it one. This is just one among them. Symplectic dilation. We want to prove a theorem that every A admits a symplectic dilation. Okay? That's what every A can be dilated to a symplectic operator. That's what we want to prove. So that is the theorem. Okay, I'll come to the theorem later. I'll write the theorem. Before that, so maybe I'll write the theorem. A is in M to N, or then A admits a symplectic dilation well, the M we will spell it out later. Symplectic dilation. Okay. So I want to give this assignment. Prove that every A in M2, M2R admits a symplectic dilation of order 4. Okay. The proof is in KRP's paper. It is just some calculation. Is specifically given some matrices. You have to verify that they are symplectic operator, and then this will just follow. Okay. And it is just some calculation. Okay, some pure calculation. It is better to write it down rather than doing it in a class. So it is very easy. You just have to. He has not verified every detail, so you just verify it in your assignment. Okay. So that's the assignment. So for n equal to 1, this takes care of n equal to 1. Okay. Okay. So we will prove for general n. We are not going to use induction, but still n equal to 1 case is finished up like that. Okay. So the proof, whatever is given in KRP's paper, write it as an assignment. Okay. So now we want to prove some sequence of lemma leading to the theorem. Okay. The first one is to direct sum. So lemma 1. If AI in MNI or admits symplectic dilation of order. This is 2, of course, 2 Ni plus Mi. Okay. Then direct sum Ai, of course, which is in M over summation Ni, of course, summation 2 Ni or okay, admits we just have to take the direct sum, but then some permutation is needed. We have to justify that. Symplectic dilation of order summation 2 Ni plus Mi, where Mi comes from that original, the corresponding order. So if you take direct sum of those which admits symplectic operator, again admits a symplectic dilation. Okay. Proof. So let A equal to direct sum Ai. Okay. And let.
Sir,
yeah.
Can you scroll up where you talk about the dilation projection?
Yeah.
Like,
It is just, you can write it as a bigger matrix where it sits as the first corner.
not this, like above this.
Huh?
Above this.
Above this.
Yeah. Like you talked about general dilations. Like, above this.
General dilation? Did I?
Yeah, so there will exist P, which is a projection that P A tilde P is a.
Yeah, P tilde A P is equal to A000. I mean, A. That's what it's A.
Okay.
It is A000. That's what. That's all. It is A basically. As an operator, and it's not, it is A. Okay.
Right.
Okay. So you take the direct sum, you take the direct sum. You want to say that this admits a symplectic dilation. Okay. So let's call it A tilde is not the right candidate, but I will write A prime. A prime equal to direct sum of A tilde. So this is in M summation 2 Ni plus Mi R. Okay. Okay. Now the thing is, if you see this A prime, how does it look? A looks like this, right? A1 up to An. A prime will look like A1, B1, C1, D1, right? And then A2, B2, C2, D2, like that, right? This is how A prime will look like, right? I'm just taking the direct sum, right? This is how it will look like. But we want to get that A1 up to An on the top. So we have to permute it. Okay. So now note that this is another general observation. Note if A admits symplectic dilation, then L1A, L2 admits symplectic dilation for L1, L2 in SP2N. Okay, where A is in Mn. Okay. So if A admits, then you can multiply by symplectic operator. That also admits. That is just clear, right? If A tilde equal to some A, B, C, D is symplectic, then you can add something, like, I mean, you can just, so this C, this M, we don't know. You can take something like L1 tilde, A, B, C, D, L2, L1 prime. Tilde is confused, right? L1 prime. Okay, so this is equal to L1A, L2, right? That is what you will do, L1A. And then if you have L1A, when you multiply with that, right, that's what you get.
You get L1A, L2.
L1A, L2, and something here, right? That doesn't matter. And then, but then multiplication of so this is already this A tilde is a symplectic operator. This is symplectic. This is symplectic. This is symplectic. So the product is symplectic. So it's clear. So you can, so if you multiply some operator by, I mean, you have to choose that L1 prime L1 as symplectic operator. Of course, it exists in M cross 2M matrix, right? That of course exists. Okay. Okay. So because of that, now if you, so now you have, so the coming to the original problem, we have a direct sum of operators, A1 direct sum of AI, where each AI admits a symplectic dilation. Then you take the direct sum of those dilation, AI, which is again a symplectic operator. See, even so, let me, so for this I forgot to remark. Even in the definition, you notice that you need, when you want to write it like this, talk about symplectic like this, you need to use this J2N, not the earlier one, right? The earlier one will become minus I, but the A will be here. I mean, doesn't make sense, right? You need to have this, this is the right definition. If you just think about it, this is the right definition. You need to have this J2N, you need to have this, right? Because this acts on some sort of R2N, which is like C2N. So C2N should be here itself. You can't get the Y part here, right? So it has to be like that. So okay. So when you take the direct sum also, okay. Now the point is you want to get those A1, A2 to the top. How do you do that? You can interchange the A2, B2, that whole row. I mean, it's not single row, it's a row of matrix. A2, B2, that row to the top. You can bring the C1, D1, right? But then that map may not be a symplectic map. But then you again do the interchange the columns. When you interchange both the row and column, notice that, so this is the point. If U is a chief, so that will be given by some unitary, okay? If U is a unitary matrix, if U is I mean, it's a U is a unitary, and this is general, okay? M2NR, okay, unitary, orthogonal matrix, not unitary, this is a real matrix, so we call it orthogonal, such that UJ2N, U transpose, or U transpose, whichever you want, okay? U transpose J equal to J2N itself, okay? If it is U is such a unitary, okay? Then L is symplectic, implies U transpose is also symplectic. Okay. So here I'm going to use the permutation matrix. I want to interchange those two rows. Okay. Where did I write that? It's here. I want to interchange the rows where we have this A2, B2 and C1, DN. Those two rows you want to interchange. That is going to disturb the J. That is not going to preserve. I mean, you want to interchange, see, when you want to say permutation matrix is a unitary matrix. If you apply, it will permute the entries of the, the tuple, the Rn tuple or something. In the matrix, you have to apply U transpose, right? That's what the add map, which we discussed. That's what you have to apply, right? So I will not write all those things. You have to apply the add map. Okay. Now, if you apply the add map, if you apply the add map to the J2N, that will get disturbed. Okay. But then when you interchange the column also, the J will be preserved. When you apply two permutation, when you interchange those two rows, which contain C1, D1 and A2, B2, then you interchange the, D1, these two columns, that is going to, you can see that preserves the J2. Since that preserves the J2N, if you apply that unitary, it will lead to this A tilde will lead to another symplectic thing. And that will have the original A1, A2 up to this. Yeah. I mean, I have said it only for 2 cross 2. I mean, in the when the direction is just two directions. For n direction, you have to make several permutations. So the rows and columns. If you do a row and then the column, then the J is preserved. J2N is preserved. Because J2N is preserved, it is going to take this add map is going to take a symplectic operator to a symplectic operator. Okay. So So similarly, so if I write, if U naught is the unitary, is the orthogonal matrix, which takes this thing, this whatever this A tilde, whatever we have preserved A prime to this map. A1, we have to get A1, I mean A1, A2, I mean A1, what will get A1, we will get B2, B1 or something. What? If you interchange A2 to the top, and then we will have B1 only there, and then we'll bring the A2 here, and C1 will remain, right? A1, B1, no, we will interchange that also, no? No, it will get the 0 itself. Sorry. No, the whole thing will go. It will look like this. You will get only zeros here, right? And then something here, something here, something here. That's what you will get.
So, like basically, reordering the direct sum, like, that's what you're doing.
Yeah. No, I have taken, this gives the direct sum like this, right? And then I am permuting it so that I get the A1, A2, that part here. And when you do the permutation, interchange of rows and columns, those B1s will go to the other side. B1 and D1 will go there. And similarly, okay. So you will get A1, the only, I mean, zeros elsewhere, you will get the direct sum only A1. Okay. So if that is the orthogonal matrix which takes this to here, then U naught, A naught, A tilde equal to U naught A, I mean, that U naught preserves the, I just want to write it. I want to write that U naught J2N U naught transpose is equal to J2N itself. Okay. Hence, U naught A tilde U naught transpose is symplectic. Equal to, this is what we called as A tilde is symplectic. Okay. I'm not writing. This is just the interchange of rows and columns so that you get this direct sum. It's clear what the map. Okay. You can write it if you spend some time on that. You have to write some more sentences. Okay, so it's clear. So we approved this lemma that if you have a direct sum of is fine, no, there is nothing more. Yeah, is okay. So if we have a direct sum of operators which admit symplectic dilation, then the direct sum, and if we take some collection of operators which admits symplectic dilation, then the direct sum also admits. Okay, this is number one. Number two, next lemma, lemma one. This is lemma two. So if we have A1 up to AN admits, so they are all in AI in MNI or sorry 2. You should always have a 2 there, 2NI, okay, 2NI or I equal to 1 to K, okay, I equal to 1 to K admits symplectic dilation of order 2NI plus MI. Okay. And we have Pi greater than 0 and summation Pi equal to 1. Okay. Then the convex linear combination, summation Pi AI, okay, admits symplectic dilation of order summation K into Ni. I think it is just, I forgot. There has to be a 2. Whenever I said that admit Mi plus Ni, there has to be a 2 there. I think I'm forgetting. So if you, yeah, 2 is there. So here, yeah, I have written 2. Okay. So this will be two K Ni plus Mi. It's a big number, but still it is finite. Okay. I mean, there are questions about minimal dilation. What is the minimal dilation we can achieve on all those questions? And it seems many of them are open. Okay. So you can work on it later. We do, the number may be very big, but we do get a dilation, symplectic dilation. Okay. So that's what this says. Okay, the proof. So, okay. So let A tilde equal to the direction. Let us take the direction first. Let A be the direction. Let A tilde be the symplectic dilation of AI, okay, of order 2ni plus mi, okay. And we want to talk about that convex linear combination, not direction. It's a complex convex linear combination. It will be, let us denote AI tilde to be A1 tilde, A2 tilde. Huh?
What is PIs?
PIs are numbers. Convex linear combination is it?
Like PIs are of different sizes.
AIs are different sizes, so it should be same size. It cannot be different size. You are right. Good. Okay, so this is M2N of yeah, it cannot be, sorry, it was a mistake. So then there is no this thing, right? Yeah, I think it is just this. Yeah, it is just this. Yeah, this is okay. It's not too big. I mean, each AI may have a MI, different dilation, but then you can make it uniform. You can take the maximum of the MIs and make it uniform. Add something, and then, okay. I mean, you can add a symplectic operator or something, you can get a uniform. Identity is also symplectic. Okay. J is also symplectic, for example. Okay, you can add anything you want. Okay. So, okay. So now you
need all of them to have the same symplectic dilation of the same order.
Yes.
that's what I said. You will same order. That's because you can add something. You can take the maximum M. Each AI will may have MI. You take the maximum M. You add some direction entry and do that. That's what I'm saying. Okay. So let A tilde be this. Using this, we want to. So this is already. This is in 2k. There are there are k of them. Okay, 2k into n plus m. Okay. Right? This is the direction. We already got some A tilde here. This will not give the required dilation because we want to get that first part. We want to get the A1 summation PIA. So how to get that? So let U to be such that root of P1 to root of Pn. And you have something here. You have something here. That is, U is an orthogonal matrix satisfying the first row is given by that. Okay. U B. Okay, let's call it U is an orthogonal. It is in MKR. Okay, tell me.
Can't we use the elementary matrix which multiplies some number and adds it to?
multiply this big matrix, no? That's what we're going to do. That's what we're going to be getting the right matrix. That's all. Be orthogonal matrix with U1I equal to square root of Pi. Okay? I equal to 1 to K. U is a K cross K matrix, and the first row is square root of Pi. And you know that summation square root of Pi squared is summation Pi, which adds to 1. Okay. So this is a unit vector. P1 up to Pn is a K cross K tuple. It's a unit vector. So once you have a unit vector, you can construct an orthonormal basis. You just collect that orthonormal basis, write that orthonormal basis as a matrix. That will be a unitary matrix. That will be orthogonal matrix, right? That's the property of orthogonal matrix. The rows are orthonormal basis. Okay, so you can construct an orthonormal basis and you can write it. So you can always get it. Okay, so you take a orthogonal matrix like this. Okay, then define S tilde, maybe S tilde equal to Uij I Un. I mean, you take the Uij, which is a scalar, and then, I mean, you want to write a 2k n plus m. This is a I n plus m. See, this is like this. U tensor identity. Or I tensor U or U tensor identity. I think U tensor identity. Okay. This is a matrix in mk tensor m 2n plus m. And this you can identify with mk 2k n plus m. Okay. So this is just the first entry is the big matrix 2n plus m identity multiplied by a scalar. Each entry is a block like this. Okay. Okay. So this is in m 2k n plus m. It's a big matrix like that. Okay. Where you are just having this scalar. Now the claim is S tilde is symplectic claim. So S tilde means you have to write it as S tilde transpose the J of the big 2k n plus m. You have to use this and S tilde. If you want to look at the ijth block, we will consider blockwise multiplication because this is just scalars in the block, and J is also just J. I mean J2 n plus m, J2n plus m, J2n. That's how J looks like, right? J2n plus m, J2n. It's like this. Okay, that's how it looks like. So, but then it's block diagonal. It's not diagonal. It's block diagonal. J is block diagonal, right? So, if you want to take the ijth block, is the block, not ijth entry, ijth block. Okay, ijth block is going to be S tilde ik. Okay, J, whatever, the J2k n plus m, whatever that thing, and it's K, but then it's only KK only. It doesn't K prime, K has to equal, for it to be non-zero, it has to be K prime, right? And then you will have maybe Ki. This is Ki. I mean, we have to take the transpose, no? So you have to take the transpose. So that's why Ki. Okay, and here it will be again Ki, right? But then this will be just J2k n plus m. These are all just scalars. Jk, the block is just the scalars. So you will have the summation over k. Yeah, one second. Yes. Yeah, skj, correct. Xkj. Yeah. But then this J2k, k is just a same matrix, right? right? It's the same matrix. No, it's KK. It's a now it's KK is, I mean, instead of a scalar, you have a matrix. Okay, and it's the same matrix, right? And so you don't the scalars you can take it that side, right? It is just the scalar. So if you just multiply the scalar x k I k s k j, that sum is 1 because that is square root of, right? I mean that comes from unitary. So this will be just the J matrix, J to n plus m. I mean, this J to K, this K, I mean, sorry, so I should use L. I'm sorry. There is another confusion because there is this K is fixed. We have fixed a K, so there should be some L or something. This Li, and here it should be LL, right? LL, and all this JK, LL are same, and you will get the same JK.
Why it should be F there?
On top one second. No. Another thing is no. If L is not equal to L prime, that is 0, right? That I should say. Yeah, when L is this is only so you only have the summation, right? Yeah, you will have the summation S tilde Li S Ij Lj. Okay, this summation is going to be this L prime Ij prime. Only when I equal to J. Only when I equal to J, this summation is non-zero, which is equal to 1, because it's unitary, otherwise it's going to 0. So this is going to be delta Ij, this J matrix, 2n plus m. Okay. This is equal to J 2n plus m, always, for all K, for all J. Yeah. This J 2K L plus M is the J matrix of the dimension, which has diagonal LL prime is the diagonal LL prime, which is
so like over here J2L n plus M is you're looking at it as J2n plus M tensor IL cross L.
Yeah, correct.
That's what, right?
Right.
And then
right. That's fine. So I'm just directly computed the product. Yeah, it will work. Okay. So it's going to get the J back again. So this implies that is symplectic. Okay. So this is proved. Okay, this is clear. So this implies you take the S tilde, whatever that S tilde transpose, the original A tilde S is also symplectic. Okay, and the 1/1 entry S tilde A tilde S, the 1/1 entry, the 1/1 block entry, okay, is summation Pi AI. You just have to write it, okay? So this is the dilation. So is this, hence the dilation. Okay. That's all. Okay, so this is clear. So we will go to the next lemma. So this is clear, no? We'll go to the next lemma. So next lemma, so from this convex linear combination, we have a corollary to this. See, if something is a symplectic matrix, constant multiple of that is also a symplectic matrix, right? Okay, you just have that, not the constant multiple. Yeah. No, constant multiple is not symplectic. If A admits a symplectic dilation, then the constant multiple of that is also admits a symplectic dilation. Okay. So why is that true?
Take 1 by C of that. And
1 by?
Like if it's C times A, then 1 by C of B admits a symplectic dilation.
Say it again. If A admits symplectic dilation, the same order, okay, symplectic dilation A tilde, okay, then Ka admits symplectic dilation of so what is the symplectic dilation? So you want to have Ka. So you already have multiply by the See, the symplectic matrix will have determinant 1. So we have to have determinant 1 somehow, right? Indeed, in the assignment, you can add one more thing. The 2 cross 2 symplectic matrices are those with precisely, where did I write the assignment? I will add to the assignment. Please, you also add. So this is assignment 1. Two SP2, okay, or for 1 cross 1 is exactly equal to SL2 R. You know what is SL2 R? All those A in M2 such that determinant of A equals 1. Of course, if it is symplectic, determinant A has to be 1. This is true for any N also. Here, if it has determinant 1, it is symplectic. You just write the calculation, you will get. If you write the property that A transpose J, A transpose equal to J2, A transpose J, A equal to J2. A transpose J2, A equal to J2.
For multiple of the matrix, we could multiply it by something like K0, 0, 1 by K, like K times identity.
K0, say it again.
On the off diagonals, it's 0 and 0. Here it's K times identity and then it's 1 by K times identity.
Where you want to add?
Yeah, I mean,
Yes.
okay, not the identity, like it goes for 2 plus 2, K0, 0, 1 by K. So,
say it again. You want to have Ka here. What do you want to add here?
okay, so
I don't understand. He does say
Isn't like P A tilde P equal to A?
P.
So you can't just multiply K everywhere on both sides.
No, I'm not sure.
something is like for 2 plus 2, something is K0. This will be multiplied by 1 by K here. And this will be some of the things. Like 0 here, so it won't be added.
No, that is not true, I think. K is, does not, no, that is not true. What I said is not correct. PA admits symplectic dilation, Ka need not admit, I mean, it is true because we are going to prove for all matrices, but a priori it's not true. We don't have a direct proof. But when we prove something else, it will follow. Okay, so this is not true. Okay, so, okay, I was wrong. I'm not wrong. I was not wrong in the sense that this doesn't follow from this. Okay, that's what I want to say. It doesn't follow directly. Okay. For example, when we prove any symmetric matrix can be dilated, then of course K times a symmetric matrix is symmetric. If you prove a strictly positive matrix can be dilated, then K times is strictly positive for positive thing. Okay, so that way it follows. Okay, not by this. Okay, when we prove general theorem, it follows. Not directly. Okay, not directly. So okay. Good. So this is not the, what's happening here? It disappeared completely and it's coming. Okay. So next thing is for strictly positive. So some, it's not true. Only for convex linear combination, we have the lemma now. Okay. For general sum, we have to wait. Okay. So next lemma. So A is strictly positive. Strictly positive means that is, of course, we know that xi is I is strictly greater than 0 for all xi not equal to 0. Okay. Okay. Then A admits symplectic dilation. Okay. And this follows from what we have done already, the Williamson theorem. Of course, we stated what is Williamson theorem? It has, I mean, it's like symplectically we can diagonalize something, right? So using a symplectic operator, instead of unitaries, you can use symplectic operator, but then we'll get a double diagonal operator. But then what earlier we got is d1 up to dn and then d1 up to dn. Here it will not be like that. d1, d1, d2, 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 you have to write because we have changed the notation. We have changed the whole thing. So A is strictly positive. We have Williamson theorem for strictly positive maps. Okay. Strictly positive. Okay. Then there exists L symplectic sp2n such that so I should write the order also. A is strictly positive. Then A admits a symplectic dilation. A is in Mn. R. Okay. Then A admits a symplectic dilation of order and 4n. Okay. Just the double. So there exists a L symplectic such that L transpose AL looks like D1 times I2, D2 times I2. It's like this, Dn times In. Okay. 0 elsewhere. Okay. Earlier we had D1 up to Dn, the first part. It's not here. We have to, because we change the notation, it will look like this. Okay. This is the new Williamson theorem, and it's clear because we are applying the unitary to everywhere. Okay. Because of that, we get this. Okay. Now we know that. So assignment, you have to prove this assignment. Assignment implies D1 I2 can be dilated to order 4 symplectic operator of order 4. Okay. Now we know that direct sum of symplectic operator is the direct sum of matrices, where each matrix admits a symplectic dilation is the direct sum also admits a symplectic dilation. Okay. So because of that, it follows. So each D1 I2 can be dilated to a symplectic thing. So this implies L transpose AL can be dilated. Symplectic operator. Okay. Now A tilde equal to L transpose inverse A. I mean, we simply say, let's say B tilde. We call that as B tilde. B tilde L inverse is the required dilation. Okay. When we say dilation, it is symplectic dilation. We are not dealing with other dilation of the original A. Each entry can be dilated, so the direct sum can be dilated. So this is true. Okay. So the next lemma. I'll go up to 730, right? So the next lemma is any symmetric matrix So here it should be, because there are two of them, so it should be double the size. Okay. Any symmetric A in M to N R can be symplectically why is there is a lag dilated to order of order 8.
Dilated to order.
Dilated to can be dilated to a symplectic matrix of order. I mean, if you are so worried about, okay, that can be dilated to a symplectic operator. Because of sharing, there is a lag here. Symplectic. When I write here itself, I see a lag. Is it because of some problem or? Battery. How much battery is there? Doesn't show the battery. Okay. Okay, let's see later. Order 8 and proof. So you want to write a symmetric matrix as difference of two strictly positive. Of course, the symmetric matrix should be non-zero.
Positive plus minus.
Yeah, positive plus you can take, but that will not be strictly positive. If you take a matrix, so you will take the, I mean, you can diagonalize it, and you will have the. See, so this is the thing. If you have any A, then A looks like U diagonal, lambda 1 up to lambda n U transpose. You get taking the positive eigenvalues and then apply this U, you get one A1, which is positive. Negative eigenvalues, you get the minus of that will be another positive. The difference will be there. But the problem is that will not work. That is not strictly positive. Okay. But you can still, if you want, you can add something and do that. But we will better do the following. So there exists always, you can write, say that.
No, simply for the radialization, you get matrices in M2C. So
No. For orthogonal, I mean, symmetric matrices can be diagonalized in M2 and R. We stated it, used it several times.
Like if it's an eigenvector, it will be
that is fine.
Yes.
But it will be unitary.
Yeah.
The unitary can be chosen as orthogonal matrices. I mean, this is the standard theorem you can look at. Okay. So real matrices can be diagonalized using orthogonal matrices. Okay. We stated in the first class or something. Okay. We used it many times. Okay. Proof. So what we do is the following. Notice that any matrix A, symmetric matrix, any symmetric matrix. This is operator inequality. A is less than norm A time. There is a lag. A is less than norm A times 1. Greater than minus norm A times 1. This is operator inequality. That is norm A 1 minus A is a positive operator. And also norm A times 1 plus A is also a positive operator. That is just clear, no? You just write the inner product. This is just positive. You just have to write xi and it is clear. A xi is less than or equal to norm A, right? Right. Okay. Is that clear to you? A.
Yeah, I mean, like I've seen it as
Norm A times I square, which you can write it as norm A. I mean, norm.
like I've seen it as A star A is less than equal to norm A square. But I think this, because it's symmetric, it would be good for it.
A xi is less than or equal to norm A times xi, norm xi square. Okay, because of that. Cauchy-Schwarz says that A xi is less than or equal to norm A xi times norm xi. Okay, norm A xi is less than or equal to norm A times norm xi. This is Cauchy-Schwarz and the operator inequality, okay, the uniform other inequality. So because of that, it follows. Okay, but then if you want, you can add an epsilon and make it strictly positive. So there exists. Okay, so there exists lambda greater than 0 such that lambda 1, the 1 is the identity operator, minus plus or minus A is greater than or equal to 0.
The second inequality would also just take it off as for the same inequality for minus.
Same inequality for minus A. Okay. Yeah. Sure. Okay. So, okay. So there exists lambda. You can add an epsilon if you want. Okay, and make it strictly positive. So I wanted to say strictly positive. Can make it strictly positive. Okay. Okay. Now A is equal to half of this, right? Lambda plus A minus half of lambda minus A, okay, which is a convex linear combination. By earlier lemma, which is a convex linear combination. So this implies by lemma, by earlier lemma, maybe second lemma, A admits symplectic dilation of order. So this admits, the first one admits, A admits symplectic dilation, lambda plus A will admit the, right? No. There is nothing in now. A doesn't admit. For us, this is strictly positive. We are only talking about A. Sorry, we want to get the theorem for A. I'm just got confused unnecessarily. We want the theorem for A. Lambda plus A is strictly positive. So that admits a symplectic dilation. Lambda minus A is also strictly positive. Okay, that admits a symplectic dilation by the earlier lemma. So the convex linear combination of that admits as a symplectic dilation, which is A, okay, by the earlier lemma. Fine. So they admits this. So lambda plus A admits a symplectic dilation of order 4n. That is another 4n. So there are two combinations. So it should be 8n. Okay, of order 8n. So the earlier one, k times n plus m you will get, right? K times 2k times n plus n. So you have to multiply by 2. Okay? You have to multiply by k, which is 2 here. So you get 8n. Okay. So this is done. Okay. So the next one, this is the last lemma, I think. For off diagonal, this skew symmetric matrices. I thought I would prove the theorem today, but I'm.
So how is this a convex combination?
How is the convex combination? This is because there's a minus, you are saying.
Yeah.
Okay, if A admits a symplectic dilation, minus A admits a symplectic dilation. Because L is Okay, plus minus half. Okay. Okay, half. Okay. Lambda minus A admits. So minus of that also admits. Good. Good question. This is convex linear combination. Okay. You just have to take minus A and change everything. I mean, L is symplectic, minus L is also symplectic. Okay. Because of that. And I mean, which you can verify from the original definition. Okay. The final lemma. If let A equal to 0 D minus D transpose, okay, is Q symmetric matrix, admits a symplectic dilation so D is in M2, okay, symplectic dilation of 8 order 8, right? Order 8, I think. Actually, there is really nothing. D is in, so proof. Order 8, let's come to that. D is in M2C, M2R, okay? So by assignment, which are a direct calculation, okay? By assignment, there exists D, E, F, G, okay, in M4 or symplectic, sorry, maybe I'll write spin group itself. SP4, okay. Okay, there exists E, I mean, there exists EFG, that's what it says, okay. There is a symplectic dilation of D, okay. Now, so this is another assignment I want to give. This is just multiplication. I can multiply. It is just a big matrix. It's better you multiply, okay. There is no point I multiply and you are not going to get anything. So what we get is the following: 0 D transpose 0 E 0 F transpose F 0 E transpose. There is a minus here. There is a minus here. Okay. Finally, G 0 G transpose minus G transpose 0.
So what's the first assignment?
First assignment is 2 cross 2 matrices.
No, like the first thing which you wrote there.
I'm going to write.
Okay.
I'm going to write the last assignment. Okay. Let me just look at it. G minus GTF. It is in the paper anyway. So I have written it correctly. Okay. FE. Here it should be F and D. Oh, here it should be the other way. Sorry. Zero. Is symplectic. You just have to multiply and verify this. You take the transpose of this, of course, that will become 0 D transpose. No, 0 minus D transpose.
The assignment is for every like simple.
Every, yeah, given D, E, F, G is simple. Okay. What happened to the old recording? Okay, now you can see that D minus D per is there, and it is just the dilation. Once you multiply and verify this is symplectic, this is indeed the dilation. Okay. So we will prove the theorem in the next class.
This matrix is there in the paper.
Yeah, it's in the paper. And I have written it correctly. I just copied. And you can, yeah, it's in the paper also. He has also left it as multiple. Ask you to multiply. Ask the reader to multiply. Okay.